Okay, so let's start today's lecture. So last week, I did define what the general framework for topological recursion was. And I started to discuss the simplest example, which is the case where you just have what would be one branch point, so what I call capital N equals to 1. And where you've got the simplest ingredient, meaning that omega 01 is just 2z squared dz, and omega 02 is just dz1, dz2 divided by z1 minus z2 squared. What I did derive in the last part of the lecture is that if you run the topological recursions there, then you get that the omega gn, which are produced in this way, can be written like as a series in 1 over zi square, whose coefficients c are constrained by the topological recursion equation. And this gave me an equation on this coefficient, which is that, I don't want to write it down again, but you should have it in your notes, which is a constraint in these c's. Now, if you've got them in your notes, what you can find out is that there is another way to represent some constraint on these c's, which is the following one. So here I did get them just by looking at the expansion of the omega gn I'm producing by topological recursion in z1, zn, when all the z's goes to 0. Now, what I will do is that I will now build another generating series for the same numbers. And I do it in the following way. So this generating series, I call it z. And what do? I take, once again, the same sum over k, k1, km greater or equal to 0, of ck1, km, g. Now, what I will do is that whenever I've got a k1, so it's k1, I will use another notation for that. Should have prepared for it. So this I will use another notation which will become clear in the following. So I've got my index G, which is for the genus. And whenever I've got K1 to Kn, I will call it tau K1, tau Kn. Now, what I will do is that I will build another generating series for these numbers. Now, what I want to do now is that in order to get these numbers, I will consider the following notation. I take exponential sum over k, tk, tau k. So what I mean by that is that I consider the expansion of this exponential when t is small, k equals 0 to infinity. Which by definition is what? You just make the expansion here. So you can have an arbitrary number of factors. So you can see it as the product from k ranging from 0 to infinity of exponential tk tau k. So it's a sum from m ranging from 0 to infinity of, and now you expand your exponential, t0 to an arbitrary number L1, so it comes with a T0 divided by L1 factorial, and you sum over L1, ranging from 0 to infinity. So I'm just expanding the exponential of T0 times tau 0. Tau 1 to the power, I should call it L0, sorry. To be consistent, it's going to be easier. And I sum over L1. Some factorial here. And so on. So I can have an arbitrary number of them. degree G. And now what I could do is just, instead of having this infinite sum, what I will consider is the sum from m equals 0 to infinity of the product from k going from 0 to m of exponential t k tau k g, which, if I use exactly this notation, is a sum. Yeah. Sorry? So that's what I will do now. I mean, I will transfer it from this one. From the thing above. Just you just take this one. So this you can think of it as a product. Yeah. So this is the product of one class. So what's your point? Yeah, I agree. But what I would like to mimic is this one. So I would like to have an infinite number of times. Yeah, this one, you mean? But the point is that in the C's, I just want to have a finite number of them appearing. So in the CG, K1 to Kn, for this one, you mean? Yeah, but yeah, okay, I just want to show where the m comes from. I mean, if I write it in this way, you don't have a finite number. No, yeah. So I wouldn't have it here, but so CG depends on some integer n here, which is finite.
There's an obvious formula, I don't know.
Okay.
That's what you think.
Just tell me.
This is by definition the sum 1 over n factorial times the sum k1
k n CGN.
0. The ck
no.
g times tk1 and tkn is trivial.
Sum over n ranging from 0 to infinity.
Yeah, of course.
Yeah, okay, but yeah, that's
But
okay. Okay, sorry. Yeah, should have done that. So I just wanted to explicitly. Okay, so what I want to have is another way to bookkeep my CKG. And so what I define is that exactly that, which I did write in this way. Sum from n equals 0 to infinity. So I'm using m usually, 1 over m factorial. Sum over k1, km greater or equal to 0. ck1, km, g, tk1. You've got some factorial here. No. Yeah, okay. Yeah. No, you're right. Yeah. Okay. Yeah, okay. Okay, yeah, that's my bad. Yeah. So this is a series in the TKs here, which are no formal parameters. I take that, and what I say is that whenever I've got a genus G here, and I've got m elements here, so m factor here, I put some h bar to the power 2g minus 2 plus m. And I exponentiate that. This gives me a function of the t's here, which are my formal parameter, and of h bar. What's your prime? Yeah. And I sum over g from 0 to infinity. No, I take the exponential of that. Yeah, I take the exponential twice, for sure. And this is a function of h bar and of the time t1, t2, and so on. You can. So C000 with a 0 here is vanishing unless m equals 3. With G, so you've got a finite number of terms. C00, it's 0 in general. For G different from 0, yes. It is. So we will see it. We will see. Sorry? So the way to think about it is to think that this will be a Poisson series. Once you remove the term constant in H bar and of order -1 in H bar, then you will get a Poisson series in H bar. So it will be of the form exponential H bar to the power -1, something plus a constant of H bar times the Poisson series. So it's a WKB type, sum over L, H bar to the power L, CL if you want. So that's the right definition. Yeah? So we'll see that later. It was just in order to be able to introduce this exponential notation. But as Don is saying, yeah, just take that for the moment, and I will explain it later. So you just take this definition. So what I'm saying is that I just take these C's. I got them because they were encoded in the Taylor expansion of omega gn when the Z goes to 0. So it was a way to get this information. Now I will just encode the same information in another function. This way, where I've got two things. I've got some variable tk, which are associated to choosing one of the indices equal to k. And I've got another variable associated to some homogeneity degree, actually, which knows about both the genus and the number of variables I've got here, which is this H bar. Okay. So that's another way to get it. Now, here, in order to recover these C's, so if I want to have Cg, K1, Kn, I would have to compute residue of this omega gn when all the Z goes to 0 of a product of Zi to some power. Here, you can do it in a different way. You just take the log of Z, just look at the coefficient of some H bar for fixing the relation between the genus and the number of elements here. And you just look at the coefficient of a specific monomial in the T's. Okay. So it's very similar in the spirit. It's just another way to encode it. And the sorry? So the symmetry under the, yeah. So indeed, these C's are symmetric under the exchange. Okay. So now, why do I want to represent it in this way? It's because the relation I did get by topological recursion for the C's here, so you can take a nice a nice representation when you think of this function, and they are equivalent to the following statement. If you consider for, let's take k greater or equal to -1, you consider the following differential operator. -2k plus 3 h bar d over dt k plus 1 plus delta k minus 1 t0 squared divided by 2 plus delta k0 divided by 24 plus h bar sum over j from 0 to infinity, 2j plus k plus 1 double factorial divided by 2j minus 1 double factorial, tj d over d tk plus j plus h bar squared divided by 2 sum over sum over d1 plus d2 is equal to k minus 1. Still have this double factorial, which comes from my normalization. 2d1 plus 1 double factorial, 2d2 plus 1 double factorial, and you've got a quadratic operator. Then the claim is that the topological recursion for omega gn is equivalent to the following thing: for all k greater or equal to -1, Lk annihilates C. So it's another formulation of the topological recursion. So as I told you here, in order to extract the C's, what I could do is compute residue. And the residue computation, which gives you the topological recursion, gives you a relation between the C's. On the same way here, one other way to think about getting the C case is just compute the action of a differential operator in T. So you just act with d over dt. It will bring some C here. So if you're computing d over dt k1, let's say, you bring some C, which has one k1 in it. And if you evaluate it at t equals 0, so this is evaluated at t is equal to 0. All the times tk is equal to delta k0. All the times, all the tk's are switched off. So you consider this function of all the t's, act with this differential operator, and you evaluate the equation when all the t's are vanishing except the first one. And the idea is that if you want to get some information about C here, you just act with a differential operator, which will bring a C down. And when you take all the t's vanishing, then this just gives you a simple number 1, basically. Yeah? With the definition, sorry? In the definition, I did take it equal to 1. Here you could have a t here as a prefactor, and this would give you your t0. So the t0 is just a rescaling, which I could have put here. So you fixed it? Yeah. Yeah. No, but here what I get is just these ones. I mean, the information of the Virasoro algebra will be the same, so I will deal with the example where you put some other times here. But directly, the relations that you get for the C are exactly the ones that you get when you switch off all the times. Yeah. 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 Yeah, I agree. But the information that you get is the same. So this gives you enough information for recovering everything. So yeah, it also annihilates it for arbitrary t's. Yeah. It is true that if you write this down for arbitrary, by switching off the t's, you will get it in the same way. Just because of the structures that you've got inside. But yeah. You think of it as coming from Schrödinger equation? Yeah, transformation.
Just a linear second order equation.
Yeah.
Transform into a quadratic.
It's a bit similar to that, yeah. And the idea is that behind that, or behind this recursion, in this very specific example, you've got that. I will not talk about this, but if you want the associated curve is of this type, if you write x is equal to z squared and omega 0,1 is equal to y dx, then your y, the y you've got to introduce is this one. To that, you can associate a Schrödinger equation. h bar dx squared minus x. And you're looking for a solution to this equation. And the claim is that these omega gns, they will be used in order to get some WKB expansion of this object. So the thing I wanted to show you is that the fact that the omega gn satisfies some topological recursion, I told you that in this case it's equivalent to the fact that these C are constrained by some relation. And this is equivalent to the fact that you've got an infinite number of differential operators, which are at most quadratic, which annihilate this Z, which is something, what I will call the partition function. This is known as Phi-Raso constraint, and the reason for that is that if you look at the algebra of this operator, the commutation relation is just that it forms a representation of the Fitt algebra. They commute following this. So this is often referred to as Phi-Raso constraints. Okay. Now, why am I happy when I've got that? So one thing which will be explained actually Thursday, I think, by Gaëtan Borot, is that whenever we will have topological recursion, there is a new formalism introduced by Kontsevich and Seubelman, which explains it exactly under this form, saying that the topological recursion will be just equivalent to the data of a set of differential equations, so annihilation of a partition function by a set of differential operator of degree of order at most 2, which form a Lie algebra. So Gaëtan will talk about that. And that's actually the big structure which is hidden behind the topological recursion. Yeah? So for maps, there is a tricky thing, which is that if you want, the times that I've got here are not the times that you've got the usual one in maps. But anyway, it's a different basis. So this is very similar to the fact that you've got this Tutte equation, which are relation between your generating series of maps. And this, you can translate it into some Phi-Raso constraint, which is the action of an operator exactly of the same type, except that the T's which I'm considering here are not the weights of polygons. No, you could make a change of basis, but here it's some infinite dimensional space, so it's a bit tricky in order to go from one representation to the other. This equation itself with these TKs doesn't have a direct combinatorial interpretation in terms of maps, of the usual maps. But in this case, for this curve, it does have a combinatorial interpretation. And that's what I will tell you now, very briefly. Yeah? Was there a question? Yeah?
This also gives quadratic recursion to the C's. Not close recursion.
No, it's quadratic indices. Look at it, not? Yeah.
The way you're arguing, the
Yeah.
sum over A's and B's.
Yeah. And it will all, I mean, what we call recursion will always be quadratic, and it corresponds to the fact that you will always have operator of this type. Purely quadratic in the T's and the other DTs, plus just a linear part. I mean, yeah, if you go to Gaëtan Borot's talk on Thursday, you should see exactly this structure popping out. So this is the original example, the baby example, where you really see it coming in. Now, why am I happy about that? It's because I claim that this, the relation I got from the topological recursion for this number C They just told me that this number could be written in terms of intersection number of some cohomology classes over MGN bar. And that's what I will discuss right now. So for doing that, I will just introduce a few definitions in order to briefly introduce the moduli space of Riemann surfaces. So I'm sorry, it's going to be very fast and a bit hand-waving. I just want you to get the idea. So what I will call MGN is a moduli space. So it's the moduli space of what? Of Riemann surfaces of genus G with n mark points. So what do I mean by that? I mean that I've got a topological surface of genus G with n mark points. And I'm considering the space of complex structure I can put on this surface up to conformal reparametrization, so conformal change of coordinates. So it gives you a moduli space. So a good example is the following one, which many of you should know, I guess, which is that if you take G equals 0 and you take n points, how do you, what can you do with conformal maps? With a conformal map, among your n points, you can always choose 3 of them and put them at position 0, 1, and infinity. So it means that the freedom I'm left with is the position of the remaining points. So this tells me that basically the dimension of M0n is what? It's the number of points minus the 3 points I can fix by just conformal transformation. So it's n minus 3. So this moduli space is a generalization of that. And so it is a space which has a dimension which is well known, which is 3g minus 3 plus n. Now, this space is very complicated. I mean, it doesn't form a manifold. But what you can do, so in particular, you can wonder what happens when you go to a case where one cycle here gets pinched, so you go to a very tricky complex structure. This space is not compact, but you can compactify, and there is an actual compactification, which is due to Döhling and Mumford. Which is what I will denote from now on MTN bar. And what's the idea? What are the elements of MTN bar? So it's the moduli space of possibly nodal surfaces. Which are stable. So what do I mean by that? I told you I could reach a point in the boundary of this space just by saying, OK, no, if I've got this, if I take a complex structure such that this cycle just pinches, I get on the what would be the boundary of this moduli space, so I should include it. Now, for example, if I would do that here, I would have a nodal surface with my 2 mark points here. This pinch cycle becomes a nodal point, and I've got my 1, 2, 3 point here. So this is a stable surface. What I would say is that it has 2 components here. And this is a stable surface because if I look at one stable component and I look at its earlier characteristic, it's strictly negative. What I don't want to have is something like that. A genus 0 component with 2 special points. So, for example, 1 nodal point and 1 mark point. And the reason for that is that the automorphism group of this surface is infinite, and I don't want it. So the compactification defined by Döling and Mumford is a compactification where you just allow nodal surfaces such that each component has Euler characteristic strictly positive, strictly negative, meaning that you cannot have a sphere with 2 or 1 special point. And for a torus, you need at least 1 special point. Okay? So I could have an object like that. I could also have object like that. So for example, if I would look at that, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 mark points. So it would give me a contribution to M with n equals 9 mark points. And what would be the genus? It's genus 1 coming from this component, plus 1 coming from this cycle here. So it's contribution to, it's an element of M2 9 bar. Okay? So the constraint, which is encoded in this stability combination, is that whenever you've got whenever you've got a component which is not nodal, then it should have so if it's a sphere, it should have at least 3 special points. If it has genus 1, it should have at least 1 special point. Okay? And when I'm doing this drawing, one way to think about it is that the more nodal point I introduce, one way to get them is just by pinching many cycles here. The deeper I go in the boundary of my moduli space. So if I pinch just 1 cycle, I just go to one boundary component, but the more I pinch, the deeper I get, the highest codimension strata I will go. There is a stratification which is given by this nodal point. Okay. So here I define this moduli space, and now you could ask some questions which are the following one. I could define some cohomology class over this compactified moduli space. And you could try to integrate it. Now, I will give you some example of cohomology class I could integrate, which are some very important objects. And it's obtained in the following way. If you take a point in this moduli space, MGN bar, so here, that's a point in M2, 4 bar. So I've got my point, P1, P2, P3, P4. For each I, when I've got such a point, I can consider the, so let's call it sigma. I can consider the cotangent bundle at the point Pi. So this is a line. when I move in this moduli space, this defines for me actually a line bundle over this space, meaning that I can consider it's just a way to present things, can consider it as a family of lines which are parameterized by point in this space. So this cotangent line at the ith mark point will vary when I will change the complex structure of my curve. And this defines for you what is called a line bundle. And this line bundle, I call it Li. It's the cotangent line over at Pi, and it's a line bundle over MGN bar. So basically, the idea is just to say that for a fixed Riemann surface, a fixed point in this space, you can define your cotangent line. And now this line bundle tells you how this will vary when you move in this family. Once you've got that, a very important quantity that you need in order to describe this cotangent line bundle is its first chain class. I will not tell you how you define it, but what is important is that it's an element. So it's a cohomology class of degree 2 in MGN bar. And now, this is what I will denote by psi I in the following. Okay. And what I will do now is integrate cohomology classes in MGN bar, which are just products of these first chain classes, these psi classes. Okay? So if you don't see where it comes from, just remember that this is in H2 of MGN bar. Now, the object I will be interested in is just the following one. I just psi1, take psi1 to the power k1, psi2 to the power k2. So I take an arbitrary monomial in these psi's, psi n to the power kn, and I integrate it over MGN bar. And I will use Witten's notation for that, which is that I will denote it tau k1 up to tau kn gn. So this is just a notation for this integral. So I take the psi classes element of this H2, take a product of them, and I integrate it along MGN bar. So these are very important quantities that you need in order to describe MGN bar. Now, how is it related to what we have here? A first remark is the following one. So do you remember that we've got that the dimension of MGN bar is equal to 3g minus 3 plus n. So if you want to integrate some form along some thing which has this dimension, you will have some constraints on the degree of the form. And the degree of the form is what? Is that what you should integrate should be in h 2 times the dimension. So it means that the sum of the ki should be equal to 3g minus 3 plus n. So it tells you that tau k1, tau kn, with this notation, gn, is equal to 0 if sum over I from 1 to n of the ki is different from 3g minus 3 plus n. Now, how can I compute that? There exists different ways to do it, and one way to do it is due to a conjecture made by Witten and proved by Kontsevich, which is that if you build some z of h bar, and t0, t1, exactly as before, where you replace the c by these numbers, you write it sum over g from 0 to infinity, sum over n, m equals 0 to infinity, h bar to g minus 2 plus m, divided by m factorial, sum over k1, km greater or equal to 0. And now I use this notation, tau k1, tau kn, gn product of the tki, I ranging from 1 to m, sorry. So this is a m here. And this is the exponential of this big sum. So Witten conjecture, which was proved by Kontsevich, is that using exactly the same notation as before, so CC is annihilated by the LKs which I introduced before. And actually, this is the unique solution which has this nice expansion in H bar, and which is a formal series in the T's. So now I've got two solutions. Yeah. So yeah, with all of them. Now I've got two solutions of the same equation, and I've got unicity of the solution. So the coefficients that I will get here are the same. So it means that the CGN, which I defined, CGK1, K2, Kn, which I defined before, they are given by these intersection numbers. Sorry? Yeah, no, okay, you're right. Yeah, I think that Paul was right. Yeah, I should do it identically. The point is that you should, okay. No, it doesn't follow that directly. You need some additional constraints. So before, I should have said that the recursion is equivalent to exactly that with all the T's switched on. So now just a first thing before I talk about the Kontsevich proof, which will make the link with combinatorics. The following one. So let's take an example to show you that these are not arbitrary numbers, tau k1 to tau kn. So if you work on genus 0, you've got a closed formula for them, which is given by the following thing. It's n minus 3 factorial divided by the product from I going from 1 to n of the ki factorial. So it's just a multinomial coefficient. Because of the constraint, the dimensional constraint which is here, if you take g equals 0, you need that the sum of the ki should be equal to n minus 3. So it's equal to sum of ki is factorial divided by the product of the ki factorial. So it's a multinomial coefficient. Oh, yeah, these are interesting numbers. Now, how can it be related to maps, for example? So Witten conjecture, I mean, this conjecture, which was proved by Kontsevich, is not a trivial statement. And the way Witten proved it is by actually getting a representation of this generating series as a generating series for ribbon graph. So I don't have time for that, and I don't want to enter the details, but the idea is that you can use the geometry of your moduli space in order to map this generating series of integral over MGN bar into generating series of what is called ribbon graph, which you can think of as maps where you've got some additional information, which is basically some kind of length associated to each edges of your map. Now, how did we end up with this curve with Bertrand when we were studying topological recursion? What we did do is actually just study this generating series of ribbon graph and solve the associated enumerative problem. And we ended up with basically a deformation of this curve, which gives us that which translates the topological, which translates this equation into the topological recursion. From the point of view of ribbon graph, not of usual maps, then this VRSO constraint, this differential equation, really has a combinatorial interpretation, but it's a very non-trivial one. So this you can find it for the topological recursion side. You can find it in a paper of Ena about what he calls, I think it's Mumford intersection number, relation between Mumford intersection number of on moduli space of Riemann surfaces. So it's a bit more complicated than the usual maps. But what is striking here is that, so I started from something completely unrelated to this setup. It was this topological recursion. But the point is that the topological recursion is equivalent to this VRSO constraint, which actually encode the geometry of this moduli space of Riemann surfaces. Yeah. Sorry? No, these will be rational numbers in general. No, yeah. Okay. So this is the stop here. I think I will stop here for a break. So this is the baby example. Here you remember how I define a curve. It's exactly a local curve. It was the data of the same thing, but I can have different omega 01 with an infinite series here and different omega 02 with an infinite series here. And what I will do now in the next lecture is deform this baby case by introducing this infinite number of time just by perturbation. And I will show you what the topological recursion produces. I mean, we can ask whether the omega gns that we compute by recursion always have such a structure, if this number have an interpretation in terms of moduli space of Riemann surfaces. And the answer will be yes. And it's pretty explicit. So I will do that in 5 minutes. Now, the first thing I will do is change my omega 01. So if I'm using the same notation as before, I just add here sum over k ranging from 1 to infinity, h 2k plus 1, z to the power 2k plus 2 dz. And now I will try to see what the topological recursion means when I've got this curve. So how does it affect the topological recursion, this change of omega 01? So I didn't touch omega 02, I just changed omega 01. And if you look at what was in the topological recursion, it appears only in one one place it appears in K of Z0 Z, which was, what was the notation I had? So here there are no indices, which was the integral from minus Z to Z of omega 0 2 of Z0 dot divided by omega 0 1 of Z. I think I added 2 here. Yeah. Now, the only place where this will change anything is in the definition of this K here. And it just appears in the denominator. Now, what you can do is say, OK, I can think of it as a perturbation of this omega 0 1, where all the HKs are vanishing. So what I want to produce are omega gn, which will be a function of the HK such that they will be series a priori of the HKs which I introduce. Meaning, if you do that, you just write this under this form, divided by what? Omega 0 1, you write it as 2z2 dz times 1 plus this divided by 2z2 dz. So it's 2z2 dz times 1 plus sum over k equal 1 to infinity h2k plus 1. So I remove the 2, and I remove the 2 here and the dz, e to the power 2k. And since actually I'm just computing residue when z goes to 0 in the recursion, I can consider it as a geometric series. And that's what I will do right now. And this will give us a theorem which I think should be attributed in this case to NR and myself, which is that the omega gn of Z1 Cn computed by the topological recursion on this curve are equal to sum over m ranging from 0 to infinity minus 1 to the power m divided by m factorial sum over k1 to km equals 1 to infinity sum over d1 dn from 0 to infinity and now what do I have? I've got exactly the same type of coefficient as before. For each k, I've got 1. So product from j equals 1 to m tau kj. Product from L is equal to 1 to n tau dl. Genus G. But no, I don't have only n. I've got n plus m in session. For the tau d, I've got as before product from L equals 1 to n 2 dl plus 1 double factorial dz L divided by z L to the power 2 dl plus 2. So this is exactly the same weight associated to the tau dl as before. But now associated to this tau kj, I've got something which comes from the h, which I introduce. So it's product from j is equal to 1 from 1 to L of 2Ka Kj plus 1 double factorial H2K I plus 1, and sorry, here it's 2Kj plus 1. And here it should be a 2Kj plus 1. So the formula is the same as before, but now what I allow is the insertion of an arbitrary number of these taus. But the price to pay is that whenever I introduce a tau k plus 1, I weight it with the weight h2k plus 1 up to this double factorial. Now if you take this formula with all the h vanishing, means that I can have only m equals 0. So this sum over m ranging from 0 to infinity is vanishing. There is only one term, the one with m equals 0. It gives you back the formula we had before. Now, how can I get it? I will just use this simple observation which I did here. This introduction of the h just changes the recursion by the k just by introducing this factor, which I can write as a geometric series. C0z is equal to integral from minus z to z omega 0,2 of z0 dot divided by 2z2 dz. And here I've got a sum over m from 0 to infinity minus 1 to the power m. And what I've got here, sum over k from 1 to infinity, h2k plus 1, z to the power 2k, everything to the power n. Yeah?
Where do you put the
This one? So first, what I do is that what I did is perturb omega 0, 1. Yeah, I could have done that. Just that there will be a natural interpretation of this choice. So there are two things. First thing is that there will be a natural interpretation of this from a cohomological field theory side later on. I hope tomorrow if I've got time. Second thing is that that's the way it appears also when you make this enumeration of ribbon graph. Third thing is that if I do this choice, I naturally have this formal variable associated to the taus. I would lose that if I would associate it to the numerator here. But yeah, that's a good question. I could have done both. And so, for example, for the interpretation as differential operator, it's actually a bit more natural to do what you're saying. And you will see that actually there is a nice combinatorial structure which pops out when you do that. OK. So let me call that K0 of Z0Z. And the meaning of this notation is that if I would have switched off all the HKs, this is the K which I used in the preceding case. So that's the K I used for the curve where I didn't have any of this H. Okay? What I'm writing down here is that this new K is what? It's equal to K0 of Z0 Z plus, and I start writing down this, so minus 1 times K0 Z0 Z times this series, sum over K from 1 to infinity, H2K plus 1 Z to the power 2K, plus some other term which will be exactly the same, where here I've got some power L. and minus 1 to the power L. Sorry? L is M, right. Yeah. But okay, yeah, this one. Now, question, can I compute things with this perturbation? Can I interpret it in a nice way? So if I write it as before, so we had this K0. I wanted to write it as an oriented edge going from Z0 to Z. So that's the one I want to use here. What I'm saying is that it's the K0, 0. C, 0, C. Plus, and here you've got this series. And what I want to have is actually a graphical representation of these corrections. And I will tell you how to compute it. So let's consider the case m equals to 1. And I will make the explicit computations there. And all follows from a lemma, which is the following one, that I can rewrite this in a different way. Yes, let's write it in this way. So what do we want to compute here in general? We want to have a function of z here. And we want to compute residue when z goes to 0 of this. So what I want to compute actually is the contributions that I will get from this term when I compute the residue when z goes to 0 of this part times the function of z. So I want to compute minus the residue when z goes to 0. So the minus sign is this one of k0, z0, z. Sum over k from 1 to infinity, h2k plus 1, z to the power 2k, f of z, where f of z would be any of the functions that I use in the right-hand side of my topological recursion. So basically, this will be a function of z which has a pole when z goes to 0. Okay? Now, the lemma is that this can be written under a different form. I started with one residue. Now I can write it as a product of two residue. It's equal to the residue when z goes to 0, residue when z prime goes to 0 of k0 of z0, z, k0 of z, z prime, sum for k from 1 to infinity, h2k plus 1. Ah, sorry, yeah. Here, I've got the inverse of a differential in z, so I should have a dz square. h2k plus 1, z to the power 2k, f of z prime, dz prime square. So if you look at it, it looks like a weird formula, but no, let's represent this graphically. Let's take the right one. So the first factor I've got here is a k0 from z0 to z. So that's this red arrow. Z appears there and there. So on one side, I've got another k0, which goes to z prime. And here, what I do is that I put this h to 2k, which I will write in this way, where I represent just this type of leaf as represented sum over k from 1 to infinity, h2k plus 1, c to the power 2k. And I still have the f of z prime, which is this part. So how can I think of this equation? So I told you I want to have this, the computation of my recursion with this original, with the new kernel, write it as the original one, plus some correction. What I'm saying is that the first one is actually what? It's the computation with the original kernel, but where you add a new type of leg here. So you introduce this mark leg, which is just weighted by this number, just this series, okay? And because of this, you could proceed after that by induction, which says that whenever you multiply by this function, it just amounts to cutting your red propagator and adding some legs. So this I would write it as sum over m from 1 to infinity of the computation with the original propagator f. But now I introduce an arbitrary number of this new type of edges. Is it clear or not? So the idea is that I just want to represent the computation with the, with the new kernel as computation with the original one, but the price to pay is that I introduce some one-valent vertices, some leaves, which are weighted by just the hk. So the h, they will appear only in these new leaves which I introduce. And because of that, you see that actually this formula will follow, because now if I just look at the internal graph I can get, these are the graphs made only of red propagators, red oriented arrows. So these are the ones which compute these numbers. But now I can have an arbitrary number of insertion of these new leaves, and they are weighted by these hk's. And that's exactly what this new insertion means. So if you manage to prove this lemma, you can directly get this equation. Is it clear? So it's a very combinatorial statement. No, yeah. Yeah, that's okay. Let me prove this lemma, and it will not be very hard. What I will do is that we'll start from this expression. And what do I want to do? So I want to compute residue when z goes to 0 and z prime goes to 0 of this quantity. And I'm doing that, so I've got 0 here. I've got residue when z prime goes to 0. Z goes to 0, but further. And I want to compute that. Now, you see that if I would have first to compute the residue when z goes to 0, where does it appear? Z appears there. This doesn't have any pole when z goes to 0. If you look at the equation, this has poles when z goes to z0 and z goes to minus z0. Yeah.
You have a dz at the
sorry to do it. No, that's this one. So yeah, yeah. Sorry. No, that's fine. So here I compute residue when z prime goes to 0 first, because, and then, yeah. So it will give me a dz somewhere, and it gives me then the residue which I compute here. Yeah. Now my claim was that if I would inverse the integration contour, I shouldn't get any pole when z goes to 0, and the reason for that is that the pole when z goes to 0 just comes from this one. It's a simple pole. But I'm multiplying by something which is a function of z, which has a double zero when z goes to 0. So actually, this quantity here doesn't have any pole when z goes to 0. So I will try to make it appear. And I do that just by changing my integration contour. So I've got z prime here, I've got minus z prime there. If I look at the difference between what happened when I integrate first z prime and then z, and the one where I integrate first z and z prime, so I reverse it in order to get the minus sign, I get residue from the coinciding point. So it's equal to the residue when z prime goes to 0, residue when z goes to 0 of the same quantity, plus, and now I've got residue when z prime goes to 0, residue when z goes to z prime, plus residue when z prime goes to 0, residue when z goes to minus z prime. Because if you look at the quantity you've got here, this might have pole when z goes to z prime or z goes to minus z prime. No, this is equal to 0. Because the integrand doesn't have any pole when z goes to 0, because you just have simple pole times double 0. So star is just the sum of these two residues. But now it's much easier to compute it. Because what are the poles that you've got when z goes to z prime? So here, no z prime interaction. Here, nothing going on. The only point where it goes on is here. And this is just the integral of something which has a double pole on the diagonal. So it has a simple pole when z goes to z prime. And so it's a Cauchy kernel, actually. So the result of this computation is exactly this formula, where you place z by z prime on one side and z by z minus z prime on the other side. And the price to pay is that you will have a 1/2, which appears from the residue when z goes to z prime. And so it's just residue when z prime goes to 0 of z goes to z prime plus residue z goes to minus z prime. And here you just use Cauchy formula. It gives you the result. So just simple pole, you compute the residue, which if you look at it will be equal to 1/2. So you've got 2 times 1/2, which will give you exactly this contribution, which is, if you look at what's going on here, you remove that, you replace z prime by z in this formula, you get exactly what you've got upstairs. And the minus sign comes from the integration. Okay? So what I did is just postulate the result, and I prove it just by moving my integration contour. And this tells me actually that the result of the recursion for this much more complicated curve has actually exactly the same structure as the one from the curve where you don't have this. The only thing I did is just expand this perturbation as a geometric series, which graphically correspond to perturbing my graph by introducing a new type of leaves, which are weighted by the perturbation I introduce. OK. So we're almost there. So it was one part, but I can also perturb omega 0, 2, and I can also consider a different I and j. So the general case is the case where I've got I going from 1 to n. I've got one set of time for each of them. I've got this delta ij. So if I would just look at this case, where I just do that, what would be the correlation function? It would be exactly the same formula, I1, In. But the only thing which will happen is the following one. Instead of having 1k here, I've got as many as I've got omega 0, 2. But so they are of the type ij. But this is proportional to delta ij. So I've got just one index. In the graph I will use for the recursion, it means that I will have an index I associated to each of my vertices. And the fact that I've got the delta ij here means that inside one graph, all the indices associated to the vertices should be the same, because this is weighted by kij, but kij is proportional to delta ij. So it means that I cannot change index for my vertices when I'm inside one graph. So now if you look at it, it means that if you look at one graph where you've got I1 up to In, this is proportional to delta I1, I2, delta I n minus 1 In, meaning that it vanishes unless all the i's are the same. And now what is the weight, what is the contribution for such omega gn? It is just given by this formula where if you've got I1 as an index, you consider the time I. So here I didn't do anything more just by considering n greater than 1. If I keep this omega 0, 2, ij, sorry, and I just have this delta function here, then the result is exactly the same. The only point is that now I've got this decoration, which is a bit transparent. It just means that I've got n copies of this omega gn, which correspond to choosing which of the H deformation I consider. So one point of view on that is to say that I've got these n copies of a disk, and they don't talk to each other because of this omega 0, 2. Now I will try to have some interaction between them, and this is done by introducing this sum over KL from 0 to, oh yeah, should put it in red, plus sum over KL from 0 to infinity, PKL ij, C1 to the power k, C2 to the power L, DC1, DC2. So now the statement I made just here doesn't work anymore because I could have some edges which go from I to j here. So now I have to work it out. And before giving you the result of the topological recursion, let me give you the proof, because I hope it will help you understand the formulation of the results. So what do I have now? I've got this much more complicated curve, and the topological recursion, you can write it as the following thing: omega gn of C1, I1, In, Cn. Maybe I should from my notes. is equal to what? It's equal to a sum over graphs G, which are trivalent graphs. Oh, yeah, let's call me GGN. We call it gamma. Topology of gamma. So this set of graphs, GGN, I1 to IN, it is a set of trivalent graphs of genus G with n leaves, which have label Zj, Ij, and it has a skeleton of oriented edges. So the typical graph is this one. So you've got Z1, I1, which is your origin. And you've got a bunch. So you built a tree with oriented edges. And then you complete it to a graph with n leaves. By non-oriented edges. And one of the few rules that you've got to follow is that whenever you've got a loop inside, an unoriented edge can only link together vertices which are descendant in this partial ordering. So you look at the arrows, and the unoriented edge should be linking to vertices which are linked together by a flow of these oriented edges. So for example, I could have this. I couldn't have that. Okay. So for this graph, so this would be for G equal 1. So just one loop, and 1, 2, 3, 4, 5, 6, 7. N equals 7. Yeah. For this trivalent graph, it's just the number of loops. So you can increase the genus only by these loops. So you could have things like that, for example. So I could draw another one, which would be this one. So G equals 2, N equals 1, 2, 3, 4, 5. So you've got basically two types of loops of this type and some other one which will just link together. There are a few constraints which are non-local in order to define them. But the idea is this one. Now, you've got in addition, so here you've got I2, Z2, and so on. Each of your vertices has a label I, Z. This has a label J, C prime, and so on. And the weight of such a graph is the weight of a graph gamma is equal to the product over E equals oriented edges. So for each oriented edge going from IZ to JZ prime, you've got a K I0. So I denote by I0 of E the index I corresponding to the origin of my oriented edge, I1 of E, of Z0 of E. So using exactly the same notation, it's the Z associated to the origin, Z1 of E. So here there is no issue of orientation because my edge is oriented. Product for the unoriented edges. And for unoriented edges, I consider omega 0,2 of Z, 0 of E, I0 of E. I1 of E, C1 of E. Now here, I did choose an orientation for my edge, but this omega 02 is symmetric, so it doesn't depend on the orientation. And once I did this product of all the contribution from the different edges, I just consider the residue when all the zi's goes to 0, the z of the edges go to 0, and I do it following backwards the order of my arrows. I first compute residue corresponding to these, and this one, then this one, and so on. Okay? Yeah. Yeah, so it's the K with the full one. Yeah. So no, indeed. So the first thing I could do is, no. Okay, I will do that a bit later. But yeah, one thing I could do is remove the H by adding a bunch of leaves here. And so I would have a product of a weight coming from the leaves, and I described to you what it was, just the sum of the HKs, and you just take residues. Now, the big issue, so this is an issue which I basically addressed already. The big issue now is that I didn't perturb only this, but I changed this as well. And in particular, it makes that I might be different from J. And so what I will do is something very similar to that, which is that when I've got Kij of Z1, Z2, I write it into two parts. I write it in some Kii, what I will call KdV. So let me draw it in red. Of Z1, Z2, plus another contribution, which I will call Kij regular of Z1, Z2. So how is it defined? Kii KdV of Z1, Z2, Ij, sorry, is proportional to delta Ij. And it is just the integral from minus Z2 to Z2 of d C1 dz divided by C1 minus C squared. And so I'm integrating from C going from minus Z2 to Z2. And I divide it by omega 2 times omega 0, 1 I of Z2. So it's the kernel I would have if I would have just this curve, and it's the one corresponding to the index I. What I call regular is what is left. So it's the same thing, except that I've got, so this is equal to the integral from minus Z2 to Z2 of what I will call omega 02 Ij regular of C1 dot divided by 2 times omega 01 of C2. Omega 01 of C2 with the index J. Where omega 02 regular of Z1, Z2, it is just the regular part, just the series from K L equals 0 to infinity of B K L Ij C1 to the power K, Z2 to the power L, dz1, dz2. So in some sense, what I'm doing is that I'm splitting my kernel into a part which has a pole when Z0 goes to Z, and another part which is completely irregular on the diagonal. And so I can do the same thing for omega 02. I would call omega 02 KdV just this part and regular this part. Yeah. Yeah. So yeah, so let's put the E here. Okay, so here I've got a product of oriented edge. So I've got a starting point and some ending point. Here I've got an oriented edge. I can choose an orientation of this edge. It gives me a starting and an ending point. But since omega 02 is symmetric, this quantity doesn't depend on the orientation of this edge. So that's why I did put an orientation of on my edge, just because, yeah. In order to define some Z0 and Z1, I've got to choose a starting and some ending point. But the result doesn't depend on that. OK. So what I did here is decompose my K into two parts. And I will try to do something very similar to what I did for the H perturbation. I will try to re-express the residue coming from K in terms of the residue coming from just the KdV part, which is a part which I know very well. So my representation would be this one. My K here is given by, so going from I to J, is equal to two contributions. One coming from something which doesn't change my index, and another one coming from something which is regular, this regular part, and which can change an index. Now, let's plug it that into this graph here, this graph sum. What does it give me? It means that because the white oriented edge and actually the unoriented one, I can do exactly the same thing. They can be either red and blue. It's a sum over graph of this type where I can have two different colors, red or blue, on this. So I will have graph of this type. Let's put something like that. And the same here, so the and arrows would have something like that. So I can have graph of this type. Now, if you look at these graphs, if you look at the red cluster inside it, how do I compute the contribution coming from it? First observation is that the index here is the same everywhere. What are the weights associated to the different contribution of this red cluster? They are the weight coming from what I call KdV here, which is the weight I would take for computing the recursion on this curve where I don't have these b's here, the irregular part for omega 02. So actually, if I look at this red cluster, this is a graph which would appear in the computation of the omega gn out of the topological recursion for the omega gn for the curve where you don't have this deformation of the b. So the irregular part is vanishing. What I will try to do is really make it equal to a contribution coming from this omega gn, such a way that whenever I will have a red cluster here, I will replace it by some big vertex of valency, the number of legs getting out of this red cluster, of weight given by the omega gn I would compute on the curve without these b's, which is exactly what I did compute before. So this is expressed in terms of intersection numbers. And now what I'm left with is just a bunch of graphs whose vertices are weighted by this omega gn, and edges are weighted by this deformation, this regular part, this blue part. No, sorry? Ah, celui-là. Hop. Yeah. Yeah, inactive, yeah. So now, yeah, that's exactly what I will do. I will just decompose it in this way. Now, in order to get the right graph for computing the omega gn, what I should have here is that I should have something like that. Some red arrow, which gets out of the red cluster. This would be exactly the right graph, yeah? Because it was for valent, and this was for valent as well. What I would like to have is red arrows which goes out of there. And so what I will show is that actually I can do that just by some residue computation. I mean, yeah, I don't have much time for that. I think I will skip it, and I will just give you the idea behind these graphs. So we had a lemma before, which was that if we wanted to introduce this h, basically this was equal to sum over m minus 1 to the power m. And I was using this red guy. And the price to pay was to introduce that. Now I'm doing something very similar here. I want to have the weight of the, so this was for the H deformation. Now I'm looking at the B deformation. So it's equal to what? So here I did write it as the non-regular part plus this part. So it's equal to this part here plus, and what is left actually is something like that. You can write it in this form. An oriented edge, which is weighted just by delta ij 1 over z1 minus z2 square. And unoriented regular part, which is weighted just by the sum of the bkl ij. And an oriented edge of red type, meaning that it just comes from the nice curve without deformation. So if I would plug it back here, it means that I replace this. By that. Same here. Up. I will get this. Here I had a vertex, which I will write in this way. What was it? This one. So you can do the same for the unoriented vertices here. And you get a sum of a graph of this type, where now I've got this bivalent vertices over which I've got to compute some residue. Sorry? So yeah, that's what I do. Yeah, basically they can never branch in the sense that, how can I state it? Basically the formula will be that this is equal to, yes, that's this. So whatever you've got here and before, you've got this formula. So if you would have what I had before here, a kind of branching of the blue one, I just replace, let's put it back here. So this is equal to, and I apply this for all. Now this is an unoriented edge, this is an oriented. Okay, so maybe I will state it just before, which is that this is for the oriented edges. For the unoriented edges, the big weight is equal to the red one, exactly in the same way, plus another contribution which comes from what would be the blue one, which is now red, blue, and red. The only difference is that you don't have this oriented edge, because you didn't have it at the beginning. Now, if I've got what you had here before, two non-oriented one, one oriented one, I replace it by red, blue, red. Replace that exactly in the same way. Whoops. By red, blue, red. And here the same thing. So even if you think that there is no red answer, the vertex is of red type. Now, what I end up is a graph which is like that, where I've got a cluster of red. And the weight of such a cluster is some omega gn. So in this case, it would be some omega 0, 1, 2, 3, 4, 5, 0, 5 of I1Z1, if it's I1Z1 here. And all my external edges here, which are some Z with the same I1. Z1, I1, Z2, and so on. And the result of the weight which will be given by that is just, once again, just taking residue whenever you've got a vertex. You take a residue when Z goes to 0. So it would just be a residue of this omega Gn computed from the curve without this part. So it's given in terms of intersection number as we had before. Now, if you look at the kind of cluster you can have here, what I could do is just represent it in the following way. When I have a cluster, what can happen? So this cluster corresponds to a graph which has a given genus and a given valency, so a given number of leaves. And so whenever I've got a graph which contributes to some genus G and which has n leaves, I replace it by a vertex with a label G. So in this case, G equals 0, which has a valency 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And it carries an index, which is the index of all the vertices inside. So all the red vertices, I replace them by objects like that. Here it's genus 0, 3 valent. G equals 0, 3 valent. Here I've got a genus 1 vertex, because I've got one red loop, and it's 2 valent. So here I could have J, K as the indices associated. And they are glued together by these blue edges. The last one is this. It's a genus called 0 vertex, which is 1, 2, 3 valent. 1, 2, 3 valent. So actually, what I can do by this procedure is by replacing all this cluster by a corresponding vertex with two labels, the genus of the graph considered and the index of the corresponding vertex I consider inside. I get a sum over graphs whose vertices are decorated, and the decoration are peculiar. These are called stable graphs. So I get a sum of a stable graph, and stable means that when I look at the vertex, I need the stability condition I had for this compactification earlier, which is that if you take 2 times G of a vertex plus the valency minus 2, it should be strictly positive. Now, actually, you should really think of this stable graph, which I obtained by just looking at clusters and replacing my cluster by vertices with decoration, as degeneration of surfaces, exactly as I did in this compactification of the moduli space. No, I will not write on the formula right now. I think I will do that next week. But the output is that this sum of a trivalent graph, I can rewrite it in this form as a sum of a stable graphs. The weight of the vertices of my stable graph are given by just the omega gn computed for this curve without the b. And I told you earlier, it is given in terms of intersection numbers, this integral of product of psi classes. Now I've got just one additional information, just come from the B deformation, the deformation coming from BKL, and it is only encoded in these edges between my vertices in the stable graphs. So this allows me to represent what I had as a sum of a trivalent graph as a sum of a stable graph whose weight can be expressed explicitly in terms of intersection numbers. And it generalizes completely the expressions that I had in the case for n equals 1, so I can have just one type of index. And I did not have the b's there, which correspond to saying that I just have stable graphs, which are composed of one vertex. And this will prove to be very important in order to map it to some problem of enumerative geometry, such that computation of Gromov-Fulton invariant. So I hope you got the structure which takes you to the sum of a stable graph. And if you've got any question, don't hesitate. And I think I will stop here.